Well, I thought I could trust mine.
Okay, so we have started the recording, and I would like to start this session. Uh, Welcome everybody to the third JPEG DNA workshop. This is not the first time we are organizing a workshop, and it's actually the third time, as you see. The two previous workshops were also co-organized by Fernando Pereira and myself. We are the chairs of the ad hoc group on JPEG DNA, which has as one of its mandates these organizational workshops. The first two workshops were organized just months ago. One was a little bit over 6 months ago, on the 30th of September. And we had three speakers. One was actually Fernando Pereira himself, who explained what are, in fact, from JPEG point of view, the issues regarding DNA storage and how JPEG might help. We had a couple of very, very interesting talks about image coding for long-term storage and synthesis by Mark Antonini, and microform and macromolecules and issues around archiving by Raja Apuswamy. We had a similar workshop earlier this year in early January, where we had again three other very, very excellent speakers. Daniel Chadash presented to us an alliance that is working on DNA data storage and gave us an overview about this. There is a European project called Orleo Archive that was presented by Thomas Heines from Imperial College, who actually is coordinating this project. And we had a very, very specific example of an archival that actually used the DNA storage, but also has a lot of storage material by Alain Dufault. I leave now the floor to Fernando.
Okay, well, first of all, let me invite you, welcome you all, especially the speakers. We very much appreciate. So as Toraj said, in JPEG, we had many times these exploration activities where we try to understand what is going on in the world that may be relevant for JPEG standards. And of course, storage is very important for JPEG. There are a lot of images and video coded as images stored around the world. So this new emerging technology seems to be very exciting. And there are new challenges that are really specifically related to this type of storage. So in terms of this activity, the main objectives, as you can see here, are several. And the first one, of course, is to involve the stakeholders to understand the needs, the applications, the challenges, and the use cases. So it's very important that, of course, whatever we do lies on the real needs on the market. And so having the right people involved in this activity, telling us what are the use cases, what are the requirements, it's very important. So, of course, JPEG is a standardization organization. So all these requirements and all these applications must have some interoperability requirements, because the idea of having a standard is clearly to facilitate interoperability. And of course, we want interoperability as large as possible, trying to make speak the largest amount of application domains. And that's why JPEG may have a say in this problem by precisely facilitating this interoperability. And of course, when you look to this issue, of course, JPEG does not want to do everything. Of course, JPEG has a specific target in media representation. So we also want to understand what what part of the problem can JPEG help to bring some specifications. Of course, these would be international specifications in order we can precisely facilitate this interoperability. Okay, so it's a phased process that, of course, starts from the stakeholders, involves the applications and requirements, involves what are the precise problems that JPEG wants to address. And in the next slide, you may see precisely this roadmap. So we have basically a roadmap that starts, as I told you, with involving the right people. That's why we are here today, and we have some good right people. So involving the right people, get the right information from these people. As you see, the use cases, organize the use cases, maybe define clusters of use cases and requirements. And of course, after you have these requirements, we define the problem. And of course, another important part of this is to also to have metrics and protocols and processes that may allow us to assess the performance of the technology that we may be getting to solve the problems that we identified. When we have these requirements and we have these metrics and processes for assessment, we may be ready to issue a call for proposals. Okay, so this is the roadmap. We are, of course, as you can imagine, in this process of requirements, use cases, starting to speak about the metrics for assessment, and in some time we may decide to have some kind of call for proposals for the specific part of the problem that JPEG believes can have a say, can have an important role. So in the next slide, you can see what are the next steps. So we have already a white paper that it's quite mature, I would say. It's publicly available. We have already we have been collecting use cases and requirements, and we want to improve them. So you can really contribute to these use cases and requirements. We very much appreciate that. Of course, we are also trying to survey what are the initiatives in this domain, both industry and government, advertise all these use cases and requirements and this initiative and our white paper to the right stakeholders to attract them, to contribute, because at some stage we will need technology. And all this process of advertising the use cases, requirements, collecting the contributions of the stakeholders has been happening not only in the JPEG meetings, not only in the ad hoc group, but also through these public workshops where we invite top people in the area and we try to collect the information to improve the definition of our activity. So in the next steps, you can see how you can contribute. So of course, we are very much welcoming your contributions. Of course, it means spread the word, tell the people that this activity is happening here. So we are about interoperability. So this interoperability is very, very important for many of these application domains. And as I told you, at this stage, identifying the use cases and requirements, it's really extremely important because this is the definition of the problem. And we will have to understand what part of the problem JPEG can help. And of course, this may drive a call for proposals in the near future. And finally, if you want to, in the next slide, if you want to participate, so you have here the contacts, me and Turaj, we are the ad hoc group chairs. There is an email reflected, so there is an ad hoc group that discusses these issues. So we can subscribe. It's a public ad hoc group. Anybody can subscribe. You can see the link here. And of course, there is also a web page, the JPEG web page, where one part is dedicated to this JPEG DNA storage activity. So this is a very public, very open. Everybody is welcome. And so that's what we are doing now. And as I said, we can move now to our third JPEG DNA workshop. Again, I'm very pleased to have these three speakers. Again, this is our process of collecting information and requirements and use cases, as I said. And we are starting very nicely with Linda Tedic, that is founder and CEO of Digital Bedrock. So Linda has been a leader in media and digital preservation and metadata for quite a few years. So she's really an expert in preservation, metadata, digital production in several companies, also working at the University of Georgia. And she is really involved in this digital storage, DNA storage technology. And we are very, very pleased to have you here today, Linda, and you teach us something about JPEG DNA storage. What is your view? What are the challenges? What do you think about the future of this activity? Thank you very much. The floor is yours.
Share my screen and jump into the presentation. So first of all, do you hear me okay?
Yes.
Okay. Thank you so much. Good morning, everybody from sunny Los Angeles, California. Thank you so much for inviting me. I very much appreciate that the JPEG committee is involving stakeholders. And so I am not an engineer. So the purpose of my presentation will be giving you use cases for how audiovisual digital preservation practitioners could use DNA storage and how our work can intersect and use DNA storage in the future. I'm sorry, let me get into the presentation mode here. All right, so, everybody throws around numbers of how much data will be stored globally. And so I'm using this statistic from the IDC report, which estimates that by 2025, the amount of data being stored from all sectors will reach 175 zettabytes. Now, some people have more, some sources have more than that, but no matter what, it's a lot of data, regardless of your source. Half of that data will be stored in the public cloud, but there's also estimates that the majority of that data does not need constant access. So this is where DNA storage or some kind of cold storage could be very useful to store the data that people want or organizations want to keep for the future, but they do not need constant immediate access to. Now, to this number, though, will be added mass data migrations from obsolete generation or legacy data tape, older drives. The data that's going to be restored from those storage media will contribute to this data storage tsunami that we're going to have to deal with. So again, I'm focusing on audiovisual data. So most of these presentations or discussions that I've been involved with are focusing on media and entertainment companies and large national archives, which makes total sense because they create a whole lot of data. But on the other hand, there are other sectors, other verticals that also create audiovisual data, which I think need to be brought into the mix, because what DNA storage has the potential to do is not just store the mass amounts of data, but many of these entities or types of organizations that I listed in this bullet point, which I'll get into in a little bit, they might not have petabytes of data, but they still have a lot of data that they don't need to keep on spinning disks. They don't need to keep on tape. They could have it in more permanent storage. So I'll talk about media and entertainment companies, cultural heritage organizations, museums, creatives, other creatives other than companies themselves, corporations, which hardly anybody talks about, governments that create data itself, law enforcement, and surveillance video. So just to give context here for the amount of storage that could be created, at least something that's a bit more quantifiable. So focusing on media and entertainment company, because we do a lot of preservation work with these folks, so I can pretty much estimate how much they all, since we have several clients, how much they're storing. So a feature film, basically the digital masters would be 26 to 40 terabytes per film. Okay, so what does this mean? The graded and ungraded picture and all those acronyms and formats after it, DPX, EXR, TIFF, DCP, IMP. Okay, these are the picture masters or the DPX, EXR, TIFF that a company, a studio would want to save in order to restore or reuse this motion picture in the future. So what this looks like, just to help you if you are not familiar with these formats, is, okay, you know that a roll of film, we all at least know what a physical film, think about a 35 millimeter, 16 millimeter reel of film looks like. And so you spool out that reel of film and it has sprockets, it has frames and sprockets, and there's a picture on each of those frames. Well, the equivalent then is kind of like Back to the Future. The equivalent with digital formats in motion pictures is where it's a bunch of frames that are still images. So instead of having a physical reel of film, we have a folder. And inside that folder, a directory, is going to be a long sequence of frames of .dpx, .exr, .tif. And those are all in sequential numbers. Those are the frames, the equivalent to those films in motion pictures in the reel. And so for a motion picture film, you could have pictures of DPX masters that could be, for one title, it could be like 200,000, 300,000 frames. The longer it is, the more frames there are, obviously, the longer the picture is. So what they'll want to save, the studio save, they're going to save the ungraded picture, which means there's no color information that has been added to it through editing. And then the graded picture also, because the graded is what it will be in the color space that was used then for whatever deliverable, whatever distribution mechanism is going to be. So they usually save both the graded and ungraded. But if they go back to restore the film in the future to put it into a new color space, for example, they're going to go back to the ungraded picture elements. Okay, so that's one element, the picture elements. Then you have the visual effects. If it's a heavy visual effects film, they might want to save the original graphics, the visual effects. They will definitely save them on the audio. So far I've been talking about the picture. The audio, then you have the print masters. Print master, obviously nothing's getting printed, so that's an old term that's being used, but it's the same concept. The print master is basically the mixes, the final mixes that are then used to go with a picture for whatever delivery deliverable they need to create for distribution. The stems, though, are also preserved and saved. The stems are the individual, so think about, you have your dialogue track, you have your music track, you might have your effects tracks. Each of those tracks have their own mixes, and those are called stems. So you save those. So if you want to go back in the future to do digital preservation, to do a new restoration of a digital film, you go back to the stem and you will redo the mixes from the stems. Okay, but you save the print master and the stems. And then you might save also, this is dependent also on the organization, the project files. And the project file would be from, I'm just using two systems here, Avid for the picture, for example, and Pro Tools for the audio mixes. And so that those then would help you. Of course, you have to be able to play that certain version software for the project files in the future. I'll talk about obsolescence factors in a second. You would want to go back to those project files in order to understand how the film was edited, if you want to redo the edit or mix. All right, so that's feature films, 26 to 40 terabytes, depending on how long it is, how many elements you preserve. Television, so let's say these days people are making 10 episode seasons, that tends to be the norm. That would be 86 terabytes per season. They're again saving the picture elements, the DPX, the graded and ungraded. If it's a visual effects heavy series, they'll save those as well. And they'll save the audio print master and the stem. So it's pretty much equivalent for the kind of data they'll save. So that's media and entertainment. So then, and again, that's per film. Museums, which have time media artworks. Time-based media artworks means instead of a photograph, an image, or a painting or a sculpture, this is content, it's an artwork that moves in time. That's why it's called time-based media art. So the storage can vary on those. So museums, obviously, they're buying digital artworks. They're buying not just paintings and sculptures. So the artworks can be disk images from an artist's computer. It could be the original files used in creating that artwork, the final work itself, which might be a video copy, and then the software and application. So if it's a real digital artwork, that's going to be an application, a software. So they're preserving those. And the data there can vary from a single artwork can just be a video file up to, it can be very complicated into the terabytes of data for software applications. Libraries and archives. Now they obviously have storage, and I know that this committee has already looked to those, but they have the problem where they have both reformatted and born digital content in their collections. So reformatted means it was originally let's say an analog videotape. It was a Betacam, 2-inch quad, even U-matic, whatever it was. They digitized it. So they are dealing with that digitized analog original. And they're also dealing with born digital video that is coming across the transom into their collections. So they have a wide variety of types of content and digital files that they need to also preserve into the future. Now, those are cultural heritage and media and entertainment, which again, this community has looked at a lot already. The DNA community has been looking at. But let's now look at these other types of sectors. So corporations, again, the storage can vary. They have their marketing videos, they have advertising, they have images, and they have event documentation of their meetings or other events they might hold. And the corporations will want to store this data also into the future because it reflects their corporate history, and also for legal and regulatory reasons, for example, for meetings. Governments create data, whether it's a local, a city, regional, state, federal, they're creating data. They're recording their meetings, rather than taking minutes these days. That tends to be the norm, at least here in the US. They're just doing video recordings and saving that instead of writing notes or minutes. They have training videos that they also create. So this can be anywhere from like a small municipality might just have a terabyte of data total over time. Then you have, of course, federal archives that create data, and that can go into the petabytes of data that they are saving. So that also varies, but this is data that they will retain according to a retention schedule or for forever. Retention schedule meaning that it has a finite period of time where it will be saved before it can just be deleted or destroyed. But then permanent retention would be, it must be retained forever. And then there's law enforcement and surveillance videos. So law enforcement, the storage can vary also. So how long they hang on to body-worn camera video, for example, that depends on what was recorded. Or other surveillance video or video presented to them as evidence. So if it is evidentiary data that's going to be retained for more than 1 year, that can get into a lot of data, especially with the body-worn camera video. Now, at least in the US and most jurisdictions, if the evidence, the video evidence is related to a homicide, they must keep that forever. So that is data, and that must be preserved forever. 911 calls often. And then we have surveillance video, which surveillance video not for law enforcement, but also like banks. So for example, in the US, the FDIC requires that banks have security cameras in their banks and also at their ATMs. And so how long do they have to keep that video? Well, it depends if there was a crime that was committed around it. So we have buses, train stations, airports, there's surveillance video all over the place for bad or good. And so that has to be stored according to a retention schedule. So how can DNA storage help to store that? So DNA storage is archival storage. Okay, so not all of those zettabytes need to be in active storage. They could be stored offline in archival storage. And so I look at DNA storage as being part of an HSM or hierarchical storage management strategy. It could be the tier 3 or the offline storage medium. There's a lot of potential to do that. But what we have to talk about here and what I want to focus on is that digital preservation is more than storage. I always tell people storage is the easy part. Basically, but for digital preservation is, we look at it as all the work you have to do before to that digital content before it goes to storage, but then it is active. And so it's ongoing managed work to preserve the content. It isn't just like you can just store it and ignore it. And so this is what I kind of want to focus on in my talk here, how use cases for how DNA storage can be integrated into a digital preservation policy and processes and workflow. So one of the primary digital preservation actions that we must take care of beyond just storing content, but this content is stored obviously in content we're going to use in storage media. Let's talk about DNA as that example, is obsolescence, not of the storage media. So that DNA storage media might be viable in 500 years, but the data on it might not be. So of course that isn't the concern of the storage media itself, but it's a concern of all of us, the digital preservationists. So how can we get that data off the DNA storage? How can we manage that data that we know is stored, but we know that the data itself has become obsolete? So the digital object obsolescence vulnerability is not the media that's stored on, but the format, the object itself. What we all must monitor is, there you have the format, obviously a digital format. If it's video or audio, it's going to have the codec inside. That format requires software to render. That software requires an operating system in order to run. And then there's hardware as well that can impact whether you can play or use any of these vulnerabilities. So again, the storage media might be viable in 500 years, but the data on it might not be. And yesterday I read this article in Storage Newsletter. There was a press release about from the Los Alamos National Laboratory, and I apologize if you all know this already, but I was struck by this quote by Bradley Settlemyer, who said, that they have some of the oldest digital-only data and largest stores of data starting from the 1940s, that it has tremendous value, and they must keep data forever. Makes total sense. Yes, you must, but cool. You store that onto something that can be viable in 500 years, but the data on it that was created back in the 1940s, do you have the software? Do you know what it is? Do you know how it was written? This is what digital preservations have to be concerned with. So because of those obsolescence factors of the format of the digital objects, oftentimes archivists will transcode these objects over time into more viable formats so they can be used in the future. So in this case then, how this impacts then the storage, how DNA must be able to work with us, is where we need to be able to retrieve specific obsolete files. Now the obsolescence factors are stored outside of the DNA storage in a different system, but we need to have the random access to be able to go, we know, oh, this one tiny little coded file, a couple kilobytes, is stored in this DNA strand, and we need to be able to get it out in order to work with it, to transcode it, to copy the new version of the DNA, and we track all of those actions and relationships in a digital preservation system. Again, that is exterior to the DNA storage itself, but the DNA storage must be able to integrate and interoperate with it. So that's number one, the obsolescence of the digital object itself. Then we want to monitor the bit health through scheduled fixity checks. So all these digital objects, these digital files, if you're a good digital preservation person, you're going to be creating checksums or hashes, tracking the algorithm that's used, and you're going to verify that those bits are healthy over time by doing what's called fixity checks in the digital preservation community. You're checking the fixity of that file, of that object. So how will DNA storage impact this core principle? Because digital preservations are a suspicious species. I tell my students, you must be neurotic. You have to plan and expect the worst, and then you make plans to how to then, obviate that, scenario. So supposedly DNA storage, if it is written correctly, then it can just be stored forever, and we don't have to do fixity checks anymore. That's what I've heard some of the folks talk about in DNA, and some of the engineers and some of the R&D work. Obviously, the error detection validation while encoding, it needs to be flawless. I know that there's work on that. I'm looking forward to speakers today talking about error detection, but it must be perfect, and you have to convince us to trust you, to trust the storage, that the data is okay, that we don't need to go in and keep checking it because we won't believe you. So you have to prove it. All right. So then the third is that you want to have redundant copies, which are then stored for disaster recovery in geographically dispersed regions. So usually then, even though you have this data that's on storage that's geographically dispersed, you still are going to be migrating that new media or refresh it over time. Will we need to do that? How do we do that with DNA storage if the DNA fails? We kind of are assuming that it won't fail over time, but never say never. The only things that are really true are death and taxes, as they say. So let's see how this is going to work. You have to prove it to us. All right, so now here's a use case here about how Digital Bedrock, what we do, and how we could use DNA storage within our architecture. And I'm very hopeful that we'll do this one day. So what we are, and why I'm bringing this up as a use case, is because we are a digital preservation service, and all we do is digital preservation, and we work with it's other people's data. It's not our data. And we have a variety of different types of clients. So we do all that intensive preservation processing at the beginning, and then it only goes to storage after all of that work is done, which is why then we need to, if we're going to be able to integrate with DNA storage would just be one of the storage places that we would be able to send the files to. So right now we're writing to LTO, so I'm going to be using LTO as like a metaphor for how DNA storage could possibly work. We could also, of course, write to the cloud and DNA in the future. Right now we make 3 copies geographically dispersed. Sometimes the data is pushed to the cloud. And we accept any kind of data or format. So we do specialize in audiovisual formats just because it's large and people need more help in that area. So what we do, and what I have here on the screen is what's in orange is where I think that DNA storage could fit in. So you can just see how there are some parts of the digital preservation processes that are done outside of the storage, obviously, but then we need to integrate with that DNA storage. So The first thing we do is we want to make sure that the bits are okay when we receive the files. So we verify the client's checksums if they provide it to us. We also create and verify the SHA-512 checksums, and that's what we check ongoing for annual fixity checks. So we use SHA-512 right now. We monitor and we track which hash we use. So will there be hashes that go into the DNA storage? How will this really look? Will it be required? Will it be necessary? That's one of the questions I have. So then what we do is, again, before it goes to storage, we extract the technical and embedded metadata. It becomes indexed. So within the database, even though the files are stored offline, is where we can search for that unstructured data. And the clients themselves can also search for all of that unstructured data in their own portal. So it's reflected there. So again, this is all the metadata that's pulled out before it goes to storage. So the files can be stored in a dark archive, in cold storage, and people still know what's there and what are these files about, how were they created too. We monitor obsolescence vulnerabilities through our digital object obsolescence database, or the DOOD, that's what we nicknamed it. We actually have a patent over that. So we can still, because we pull out all that technical characteristics metadata off the files and information about how the files were created, we can do those obsolescence checks, outside of the storage system, because we do that. But we still need to be able to go into the storage to find a file if something has become obsolete or it's vulnerable. So in orange, we perform annual fixity checks on data. This is really where the DNA storage would intersect. Will that be necessary? Do we need to do that? What would that look like with DNA storage? We retain an audit trail of all actions. So that includes anything on storage and anything on the files. We write the 3 copies to LTO using LTFS. We validate each copy, not just make a copy and a clone, but we validate that each file was created without error, that the checksums match, and then we store them offline in 3 locations. We will migrate to future storage media. Now, how will this look with DNA? And critically, we implement an open architecture. There cannot be any vendor lock-in. We have to provide an easy exit. We cannot lock in our clients' data in some proprietary system, which includes the storage. So we cannot lock their data into some proprietary DNA storage where they wouldn't be able to get the data out themselves, or we can't easily get it to them if they want it. So the requirements for DNA storage to be used in an archival storage medium within an overall digital preservation strategy. These are my thoughts on what it would need to do. Interoperability, which was the last point that I raised. It also, so whatever data is written into one DNA system must be able to be read out of a competitor's system. And so this is really critical. This is number 1. If this cannot be resolved, in other words, there's interoperability between DNA coding and decoding system, it cannot be used for digital preservation. It is a core tenet of digital preservation. You cannot lock up data in some proprietary way, because that just totally negates the whole purpose of digital preservation into the future. There should be portability so that data storage vendors can read in-house. So for example, for us at Digital Bedrock, we need to be able to write that ourselves because our clients are trusting us. So we need to be able to do that internally. I already mentioned about random access. We need single file retrieval or indexing. So a client gives us a file that's just a couple kilobytes. We need to be able to pull that out. We need to know exactly where it's stored, and to be able to go in, we'll know on our system, okay, it's stored here. How can we then retrieve that data out of the sequence? And the cost, I know everybody talks about costs. Yes, it will come down. Things always come down, as it's developed. I'm not worried about that so much. But it really should be kind of what consumers are accustomed to spending today for a physical storage medium, because they will be saying, hey, we're writing this supposedly to DNA, right, once forever. Why are we paying so much money if it can just be stored offline forever and ever? So that's a consideration. The write read time must be at a minimum be 1 gigabytes per second. And I mentioned this as a requirement because, for example, we have one of those film DPX sequences, and a client will say, and that could be for a feature film, it can be like 5 to 7 terabytes. And we have to get it to them now if they need it. We can't be twiddling our thumbs just waiting for that data to get restored because it's too slow. So it has to be at a minimum at 1 gigabytes per second, and preferably more. The form factor should be consistent across systems. Again, I'm looking at the LTO data cassette model. The storage environment must be reasonable and not require cold storage. And that's for a couple of reasons, which I'll get into the next slide, for the environmental considerations, and also for the people who are storing these. It should be in a more kind of an office environment if possible. Again, looking at the LTO stored where it doesn't necessarily need to be really cold. It must have lossless encoding. This is, again, another non-optional requirement. It cannot do anything so that there are bits that will be lost from the files when they're encoded to DNA. It must be lossless. Error detection and correction must be improved. If people need, if basically the DNA manufacturers are saying like, you don't need to do fixity checks because the data was written correctly and it's going to be fine forever like that. We need proof that the data was encoded with no errors. We need to trust you. We need to gain our trust. And then critically is green technology. The physical media, because a lot of, especially the cultural heritage organizations are very concerned about this. The physical media should not be made from rare heavy earth materials. And I'm wondering, is it possible how it's going to be written? Is it possible to do it without silica sand since there's a shortage of that? Is there some other thing? And this is where, again, I'm not an engineer, so I'm looking to you for the answer for that. The right read processes should use minimal energy. And the physical storage should not require ultra cold environments, obviously, because ultra cold requires a lot of energy, which uses up Earth's resources. So again, I am not an engineer. I appreciate that you've all invited me to come and speak as, a stakeholder. I really hope that Digital Bedrock will use DNA storage. I want to go through just one LTO migration, and then after that, migrate to DNA. I'm very hopeful for this technology. I know it's kind of rough around the edges right now, but it will get better. It will improve because there are so many people invested in this, and I think it has a lot of potential. So thank you for inviting me to speak with you all.
Thank you very much, Linda. That definitely you delivered on the requirements and the number of requirements. Some of them we had discussed before, some we didn't, and now we should probably take some time and see how those that you are new in your presentation can translate into the type of things that JPEG can do. Thank you very much. I'm sure there will be a lot of questions, but because of interest of time, we have put and reserved some time at the end. So all the questions, we are going to put them at the end. If you are afraid of forgetting your questions, just type it in the chat room, and we will definitely answer to that. Now, without any further delay, I would like to invite Reinhard Heckel for our second speaker, who's going to tell us about low-cost DNA data storage, and especially in noisy synthesis and advanced error correction environments. Reinhard he has a double affiliation, both Technical University of Munich and Rice University. So he goes back and forth between Munich and Houston, and currently he's in Houston from what I understood. Reinhard, the floor is yours.
Okay, thank you very much. So you can see my screen, right?
Yes.
Okay, perfect. Many thanks. All right, so I'm going to talk about a big project that we did in collaboration with a group at ETH Zurich, and that was led by Robert Grass, Professor Robert Grass, and a group at TU Vienna, which is led by Mark Somoza. So I'm going to talk about DNA data storage using photodidiographic synthesis and error correction. So I'm really going to talk about like how can we build a DNA data storage system. All right, so we're all excited about DNA storage because it offers excellent longevity. So data lasts very long, or has the potential to last extremely long, and the information density is very high. And there are already, so the community has made a lot of progress in my opinion. So there have already been commercial applications. So for example, last year we stored a whole series for Netflix on DNA, the biohacker series, and it's stored in this fluid actually. So however, storing information in DNA is really expensive compared to storing it on tape and so on, and is also currently relatively slow. So how does the DNA storage system work, and why is it currently expensive and slow? So the way it works is roughly as follows, right? Like we are given some data as a sequence as 0 and 1s. Then we have an encoding mechanism, and Sergey is also going to talk about that, I assume. And the encoding mechanism, what it does is it takes the data and maps it to a number of DNA sequences. So that's important because we cannot write a very long strand of DNA. We can only write a lot of very short sequences. So DNA data on DNA is always stored on a lot of short sequences. So in the case of Netflix, we stored information on about 4 million very short sequences. So very short is like 100 nucleotides long, or maybe 200 nucleotides long, right? So that's going to be important. And then there's a mechanism of synthesis. Those sequences are being synthesized, then they exist in DNA, typically many copies of them, right? And then they are stored, and there might be some preservation going on here. And then once we want to read them, we sequence the DNA, and then we reverse the process. We again get a number of sequences, and then we decode from this DNA. So what makes this expensive and slow is the synthesis followed by the sequencing. So the current bottleneck really is the synthesis. So how is DNA synthesized? There are at least 3 different technologies. So there's like a printing technology. So that's used, as far as I know, by, for example, Twist Bioscience. It's very low error. So the DNA has high quality, but it's also relatively expensive. So a few cents per nucleotide. A second technology is electrochemical. It kind of has medium to low error, but it's also relatively expensive. And then there's light-directed synthesis. So light-directed synthesis works as follows. So there is a flow cell. So this green thing is a flow cell. And there's essentially like an element that shines line on this flow cell on particular parts of this flow cell. So it's essentially something like a projector, right, that we use when we give a talk online. And it can be really cheap to build such a device. So Robert Grass, he built such a device in his lab with very low cost components. So it can be really cheap to build that, but it has a very high error rates. So what we wanted to look at in this project is, well, can we do DNA data storage with such very high error synthesis by using extensive error correction? So that's what I want to talk about in this talk. All right, so what kind of errors occur in DNA data storage? So one type of error that always occurs is a loss of sequences. So that happens no matter how good the synthesis is, because because these sequences get lost. First, it might be that they are not synthesized, right? But even if synthesis is perfect, we lose sequences because of the decay of DNA, right? And even if that would be perfect, then we lose sequences through the sequencing of the DNA, because sequencing of the DNA essentially corresponds to only reading like a random sample of our DNA. So no matter what we do, we will lose sequences. So we have to account for loss of sequences. Then we have substitution errors. So substitution errors are things like that, right? We write ATA and then we get CTA, for example. So substitution errors occur in synthesis, but they also occur during storage, and they also occur during sequencing. And then there are deletion and insertion errors, and those are the meanest kind of errors because they are hardest to correct for, and Sergey is really an expert on that. So deletion and insertion errors are of the form like this, right? We might have a sequence ATA, and that gets like ACTA. And deletion and insertion errors are introduced a lot during the synthesis. So here's an example. So just so you get a perspective on the numbers. So here you see a number of papers. So Goldman, that was one of the first papers on DNA storage. Then there's our 2015 work, Grass et al. Then there's Eric and Zelinsky's work from 2017. And then there is the work by by Microsoft Research and University of Washington. And those 4 works, they all used like a really good synthesis in a way, like very low error synthesis. And as you can see, the insertion and deletion errors are really low, but there's like a moderate amount of substitution errors, all right? And in this work, we use these light-directed synthesis. And in our case, the insertion and deletion errors are just like really high. So that's the error probability per nucleotide. So 1 in 10 nucleotides is wrong. So it's like an extreme amount of errors, as you can see here. All right, but now again, so now let's think about how can we correct for all these sort of errors. So let's first talk about a loss of sequences, right? Because we always have a loss of sequences, and then let's slowly build up to how can we potentially deal with such a huge loss in deletion and insertion errors? Because as the previous talk demonstrated, we really have to enable error-free storage, right? So that's only possible if we manage to correct all those errors, right? Okay, so loss of sequences. How can we correct for loss of sequences? It's relatively easy, relatively straightforward. So there is this idea of an optimal erasure code. So that works as follows. So we are given our data in zeros and ones, and we organize it as a matrix, and then we encode it using an erasure code. And there are many erasure codes that we could use. And what the erasure code does is it adds some columns here, right? As you see, this matrix here has more columns. So we add some redundancy, and this redundancy has a property that now if we lose some of these columns of the matrix, then we can perfectly recover them, right? So that's what the code enables us to do. However, the code requires the order of the columns to be correct. And the order is lost in DNA, right? Because we write a number of sequences, and the sequences, they as shown here, they kind of float around, so they are not ordered, and there's no way we can order them without losing density. So in order to remember the order, we add an index to each column. So that's very straightforward. Then each column is synthesized, then we do DNA sequencing, and now we get a number of unordered columns, so to say. And but because we added an index, we can just sort these columns and get this code word back. And now what happened is, like, we lost some sequences, right? So these X's here, they correspond to lost sequences. But because we encoded our data, because we added redundancy, we can perfectly fill in those errors, right? And decode. All right, and sorry. So this so it turns out that the simple way of encoding and decoding is in fact optimal. So if we do not have errors in sequences, then it can be shown that just adding an index and using an erasure code is actually information theoretically optimal. So the scheme maximizes the number of bits per nucleotide. All right, but now remember that in reality we do have at least substitution errors, right? So and we also have a few deletion and insertion errors, but like even if we use synthesis that is almost perfect, we do make like a few errors, right? So now let's see how we can deal with those errors. Well, a simple way how to deal with these errors is to just add another code to also add redundancy on the level of the sequences. And so that's what this scheme here does, is we encode and we add an index to each column, but now we also encode each column. So essentially we take the DNA sequences, the ones that we actually store, and then we also encode them. So we add a little bit of redundancy, and then we again synthesize that, do the sequencing, and then we have a first decoding step, and this first decoding step enables correcting some of the errors that are introduced on the sequence level. And some of those errors will be corrected, and then we can again sort indices and remove them. And now what happens is, like, we lose some sequences. So those are the X's here, right? But some of the sequences are also not lost, but they are wrongly decoded from this first code here. So those occur as errors, but again, because we encoded the whole thing, we can remove, or we can correct those errors with this code here. So this way of encoding and decoding it's called using an autocode. So we call this first code here an autocode, and using an inner code. And we introduced this in 2015 in our paper. And it's a very natural and kind of straightforward way to encode. And the other papers that I mentioned, they also used this way of encoding and decoding. But that's something that really requires the errors in the sequences to be relatively low. So this way of encoding and decoding will not work if we have a huge amount of errors in our sequences. And remember, if we use these light-directed synthesis, then we just have like an insane amount of errors here, right? As you can see, we just have a lot of insertion and deletion errors. And just to give you some perspective, in our experiments, only 1 in 10 to the power of 7 many sequences was error-free. So pretty much every sequence, every single sequence contains at least 1 error. So lots of errors. And it's not possible, like it is really impossible to correct this with an inner code only, because the sequences are very short. So they have lengths like 100 or 200, and there are no deletion and insertion correcting codes that can correct that many errors. So it's really not possible to use to just work with an inner code. So what we have to do in this case is we have to combine many sequences. And what comes to our rescue here is that the light-directed synthesis, or actually any synthesis, it doesn't just produce one sequence. So it's not that we tell the sequencer, okay, like generate this one sequence of DNA. What the machine does is it generates like hundreds and thousands of copies of the same sequence. And in the case of light-directed synthesis, it actually generates hundreds and thousands of noisy copies of the same sequence. And luckily, the errors are relatively independent within these copies of the sequences. So what we actually have in our pool of DNA is we have, of each sequence, we have many noisy copies. And so now what we can do is we can just try to combine all these noisy copies and get like a not so noisy copy potentially, and then we can just do what we did before. So that's the approach we took in this work. So if we have a lot of errors, like many errors in the molecules, then what we have to do is we have to combine the information stored on many sequences. And the way we do this is we get our reads, right? So the reads is what we get from the sequencing of the DNA. So that's what we get. Yeah, that's the data that we get. And then we cluster those reads, and then we obtain clusters. And if we cluster well, then we get clusters where the sequences are relatively similar. So that's by the way, so that's real data. So that's not a toy example. So you can see things are very noisy. And within a cluster, we perform a multiple alignment, right? So in this case, we align those 4 sequences to a single sequence, and then we extract, we align them, and then we extract a single sequence. And to extract a single sequence, we really take the error probabilities into account. And we measured those error probabilities. And from combining all the sequences, we get a single sequence for each cluster, and those sequences again have errors, right? But the errors are much lower, and now our standard error correcting schemes can deal with those kind of errors and can correct for those kind of errors. All right, I also want to mention, so for the clustering step, we use locality sensitive hashing based clustering. So that's like a very efficient way to cluster. So it's essentially linear in the number of reads. We use an approach that was introduced by this paper here in 2020, in 2000. But I would also like to mention that the group from the University of Washington and Microsoft Research, they also have a very nice paper where they explain how you can cluster billions of reads for DNA data storage. So point being that this clustering step can be efficiently solved. Multiple alignment can also be relatively efficiently solved. And so that's a scheme that can be implemented. And the code to actually do that is all online. So we put all our code to reproduce these results online. All right, so the summary from this work is that we built this system based on light-directed synthesis and based on using a lot of error correction. And this work shows that it is possible to do reliable DNA data storage with very noisy synthesis. And it also shows, and I think that's really well known, at least to the coding community, that codes and algorithms, they really enable to shift costs from, for example, synthesis to coding, and they enable to work with very noisy synthesis or very noisy sequencing. In our case, this really leads to a cost reduction, because now we don't have to rely on this very expensive, very low error synthesis. We can work with high error synthesis that is a little bit cheaper at least. All right, and the last thing I would like to mention is that in order to build this these DNA storage systems, I think it's really critical to have this combination of expertise in information theory and coding and so on, and the expertise in chemistry. And Professor Robert Grass and we teamed up like 8 years ago to work on this, and I think that has been a very fruitful combination to essentially have like somebody who understands the information theory and Robert Grass, who is like an expert in everything related to chemistry and DNA. And other successful groups that build DNA data storage system also have this composition. All right, so here's another example of a commercial application that we did. So here we stored music for the rock band Massive Attack on DNA. So that's another example that there are already commercial toy applications at least. And with this I would like to thank you for your attention.
Thank you very much, Reinhard. Very interesting points you raised. I'm sure there are many questions, but again, for the interest of time, we are going to delay all of them to the end and move now to our last speaker, Sergey Yekanin, who is from Microsoft and is going to tell us about what they do in terms of efficient DNA data storage. Sergey, the floor is yours.
Thank you so much. Do you see the slide deck?
Yes, we do. We do see it.
That's great. Yeah. So my name is Sergey. I work for Microsoft. And at Microsoft, we have a project in DNA data storage space already running for like maybe five and a half years, since maybe sometime in 2015. And this is joint work by a large number of people. I won't go over the names of all my collaborators. I work on the coding theory side, so I'm a coding theorist. That's my background. And I will briefly summarize some of the learnings that we have in this project. So there will necessarily be some overlap with Reinhard's talk. Actually, I should have asked for slides before so that I could minimize it. But anyway, so very briefly, DNA data storage, the kind of history. So the idea of storing data using synthetic DNA molecules as a storage medium, it was first mentioned in 2 publications by Mikhail Neyman in 1965, a Russian physicist. But that has been long before any of such systems could have been really built. And the first DNA data storage system came out of George Church's lab in 2010. And since then, the field has been expanding rapidly. So here I mentioned few papers. That's very far few DNA data storage systems that have been published. this is really far from being the kind of the selection is far from being exhaustive. And the point of the selection is really like not to kind of give more credit to these people than to others, but just to indicate how the scale of the systems have been growing. Like George Church's DNA data storage system was pretty small. So they just stored 3 kilobytes and read out these 3 kilobytes, even with some errors. But then, like, we see this rapid expansion. So 2 megabytes, 22 megabytes. Our group in 2018 published a paper about a system where we wrote and read 200 megabytes, and the expansion continues. So like current people can work with even larger volumes, and hopefully we'll grow to the really right volumes to compete in the real industry space. And as it has been mentioned in other talks, the main promise of synthetic DNA is density and storage lifespan. The initial target is cold archival storage. The main issues are cost of read, cost of write operations, throughput, and it's a hugely active area. So there are big companies investing, small companies, startups, groups at universities. And again, the list of logos is just for demonstrations, far from being exhaustive. So what I want to do in the talk, so I'll have some parts of kind of very high level review of the DNA data storage channel and views of encoder and decoder. But what I'll try to kind of to focus on are really metrics. Like when we design these DNA data storage systems, so how do we know that we are doing well? Like what should be, from the coding theory standpoint, what are the quantities that we should be optimizing? So yeah, I'll focus mostly on this. The channel, and Reinhard had a great coverage of that, right? I mean, so I'll be really brief. I mean, so how do, like, okay, so we start with digital data, then we give it to the encoder. So the encoder is a digital program that converts it into a set of short strings in quaternary alphabet ACGT. Then once we have the set of short strings, we do DNA synthesis. So we get DNA molecules. And when we want to read data, so yeah, then we sequence the DNA molecules, and then we get multiple noisy reads of every molecule that we store. So, and there's multiple, I mean, maybe 0. So for some molecules, we just would have no reads. For other molecules, we will get multiple reads, but these reads are going to be noisy. And the noise that we should expect to experience are insertions, deletions, substitution errors. Like substitutions are easiest, but we will have insertions and deletions no matter which technology we use for synthesis and for sequencing. But of course, like the kind of technologies that are used greatly affects the real kind of error profile. So, so the technology that Reinhard talked about, like it introduces a lot of errors at synthesis. In other technologies, like we have pretty reliable technologies for synthesis, but they have their own drawbacks. And for in the space of sequencing, the 2 main technologies these days are Illumina and Nanopore. So Illumina is the older one; it's more established. And there, the error rate is around 1% per coordinate, so it's pretty reliable. But today, people are more and more shifting towards reading DNA with nanopores in DNA data storage applications. And with nanopore, although again, there are multiple advantages to using that, the error rate is significantly higher. So the error rate from using nanopore, it's closer to 10% per coordinate. So I mean, maybe 7, 8 more recently, but so one also just gets a lot of these insertions, deletions, substitutions at the sequencing stage. And like if one would combine it with a higher throughput but less reliable synthesis technology, the total number of errors on the strands can be really high. Okay, so as coding theorists, so we focus on the encoder and decoder design, and we try to build our system so that it's quite reliable, so that it's quite generic, so that really change in a synthesis technology, change in a sequencing technology would just kind of affect certain parameter settings that we put in our encoder and decoder, but really kind of the architecture should be generic. That's how we think of that. Okay, so and again, as Reinhard mentioned, the length of the strands, length of the strings of DNA molecules, it's usually between 100 and 200. I mean, it's true for our system, it's true for most other systems. The size of the problem, right? I mean, so when we do this encoding, so like what's the size, like how many DNA strands are we operating with? Like how many strings, how many DNA molecules do we want to synthesize? So today it's mostly like millions. But again, as the technology matures, if we want to reach the, if we want to really compete in the marketplace, then we should get to billions. So like we should work with files which are of size gigabytes. So the scale of this computational problem of encoding and decoding, it is growing, and we expect that it will keep growing for a while. And another thing to mention, and I think Linda referred to that, is that it's very important to have random access. I'm totally leaving this out in this talk just for the sake of saving time. But I should mention that with DNA data storage, there are mechanisms, established mechanisms, and there are published systems, including the one that we have in Microsoft, that provide random access. The only question is the granularity. Like if you store data on a disk, I mean, you can refer to a specific bit. With DNA data storage, your granularity of random access would likely be larger. But and again, it's a question of really system design of where you want to put it, because there are various trade-offs here. But so most likely it will be like on the order maybe gigabyte in the end, or like 100 megabytes. So, and this will basically lead to this, like that will define the scale of this computational problem that we are solving here. So because like whatever minimum kind of access granularity that you want to provide in the system would determine the size of the computational problem that you are solving when you're doing encoding and decoding. Because random access is provided by biological mechanisms, not by coding theory mechanisms. Okay, so now let me talk a little bit about the metrics. Okay, so obviously there are many published systems now, probably multiple dozens, right? Many different encoders, many different decoders, and and some of them outperform others on some trade-offs, and some are better on other, like on some metrics, and some are better on other metrics. But really, what are the key metrics that we should be pursuing? So how do we know that we are doing well, that we're improving our encoder and decoder? So we need some way to model the cost of read and the cost of write. And then, of course, like on top of that, we want the encoder and decoder to run fast, to have high throughput. So these are also obviously very important considerations. And for cost of read, I think that everybody is in consensus. And so cost of read is kind of easy to model. So it's basically like if I want to read a file of size a megabyte, then how many DNA bases do I end up sequencing? How many DNA bases do I end up reading in order to recover that file of size megabyte? So this defines as bits per base density, right? So how many bits do I get out of sequence a single base? So that's that is this that's the way that we measure the cost of read. Cost of write. So often, probably like I would say maybe in all papers, people have been looking at this measure also like bits per base on the write. So if I want to write a megabyte file, then okay, so I end up synthesizing some number of strands. So let's count the total number of bases in the strands. And if I'm not synthesizing too many bases, then probably I'm doing good on the cost of write. So, and what I'll point out in this talk is that this measure is very rough. So, I mean, it's some kind of approximation for what's really going or what's really happening, but it is a rough approximation, and sometimes it's a misleading approximation. So really, there are better ways to model the cost of write, and these have to be taken into account when one is designing the encoder and decoder. So I'll talk more on that towards the end of the talk. So now, kind of the generic architecture. So like, okay, so the encoder and decoder, how do they work? So we saw one example in Reinhardt's talk. So, and I mean, really, like this is pretty generic architecture that most of the published systems follow. Like again, some systems would deviate in one dimension or the other, but that's mostly what's happening. So the first step is that often people would randomize the data, or make sure that the data that you want to encode looks random by other means. Like you can really randomize it by say XORing it with an output of a seeded pseudorandom number generator that produces a string of the same length as the data, or you can encrypt or you can compress, but just make sure that data looks random. It's beneficial for multiple stages of the decoding process. And then data is represented in strands. So in every strand, given the strands are stored without some kind of ordering, so there would be the address and the payload. So, and the payload can carry data or redundant data. So then there are outer codes, and Reinhardt talked about them in detail. So like basically you arrange your data in some kind of metrics, and row by row you use, and here people usually are not creative. So like they would use read-Solomon codes, LDPC codes, digital fountain codes, some classical codes from the 70 years of the history of coding theory. So this, and then there are addresses attached to the strands. So that is the outer encoding. And then there would often be inner encoding. So with inner encoding, there is a lot more flexibility. So people have so groups, various groups at various institutions have been trying lots of different inner codes, many different choices here. And the point of inner codes, outer codes provide redundancy that goes across strands, and one has to use them because some strands will be missing. Inner codes provide redundancy that that is local to a strand. So, using inner codes, depending on the specific synthesis in sequencing technologies, it's not always necessary, but it can give significant benefits in terms of optimizing the metrics that we want to optimize with designing the coding scheme. And using inner codes serves two purposes. So one is just providing improved reliability, and the other one is ensuring constrained representation. So, so what is constrained representation? So really, this DNA data storage channel, it's pretty complicated. So when we say that, okay, so there are some error rates, so some strands are missing, and then there is some error rate per coordinate, this is kind of the first approximation for what's really happening there. If one looks closer, then we'll see that, the errors on strands, these insertions, deletions, substitutions, errors, they're very far from being kind of IID, from being random and independent. So we know that certain strands, just by their nature, are more problematic than others. Like if your strand has a long run of repeated characters, if it has, say, 5 A's in a row, it's much more likely to suffer errors. Errors are more likely to happen one after another. So there is kind of a spatial dependency. If your strand deviates too much from 50% in the total number of G's and C's that it carries, it's again it's more likely to experience significantly higher error rate than other strands. There is even more complications coming from something called DNA secondary structure. So there is that's a whole large direction of that's a significant amount of literature studying that. So basically, there are certain substrings you want to avoid from having in your DNA strands. And randomizing data helps to some degree. It alleviates, because then you're less likely to experience the DNA secondary structure, unusual GC content, long runs. But you can do more. And using inner codes, it helps with error correction, but it also helps ensure that you avoid at least the most problematic types of the secondary structure. And lots of details here on the inner code design that again, we won't cover in the interest of time, but I think it's important to point out the complexities here. In the decoder, again, as Reinhard has been covered to a large extent. So the first stage, and this is a generic view. So I'm a bit biased towards we do at Microsoft, but many other systems fit this at least to some degree. So yeah, the first stage that people often do is clustering. So we have these reads of many different, there are DNA strands that we synthesized, and then for each of them we get multiple noisy reads. If we randomize the data, we can kind of hope that in the edit distance space, our initial strands are kind of dissimilar, they're far apart, but then the noisy reads of every strand, they're more or less similar. So they're somewhat they're close together. And then it's great if we can do clustering, we can recover these kind of groups of reads that come from a single original strand. And there are many ways to do clustering. So some are, one thing is that it does not necessarily need to do clustering. So one can avoid this step, and then you would be less efficient in various metrics, but it's, it's also it may be still possible to decode. So, or you can cluster based on prefix. You can just look at the the first few bases at the address of the strand and try to cluster based on that. Or you can cluster based on the full content. So on the full content of the strand, that's computationally, this is the most expensive way of dealing with this problem. But on the other hand, in terms of optimizing the cost of read, the cost of write, that's the best way to do it. So, and then there is trace construction decoding of inner codes. Again, so here, the input is that we have multiple noisy reads that we believe came from a single strand. We want to recover the original strand, maybe with some Hamming errors. Ideally with the lowest possible number of Hamming errors. So, and again, a lot of deep thinking that went into that. So if there are no inner codes, then this is an instance of trace construction problem, which has been studied a lot in computer science literature. There are some kind of ad hoc codes that people have been using in the space, ad hoc inner codes, Reed-Solomon codes. Recently, significant improvements have been obtained by using convolutional codes for edit distance, and I mentioned a few papers here. So yeah, but at large, this is a step. You get multiple noisy reads, you try to recover the original strand. Then once you have estimates for your original strands, You can sort them based on the address and decode the outer code. So that is that's a high level view of the decoder architecture. So let me actually mention a little, this is one technical slide on how clustering works, and then I'll talk about the cost of the modeling the cost of writing. Okay, so what is the clustering problem? Right, so we are dealing with eddy distance, and we have this very large input. So we have these billions of points, and but we believe, like, we have this promise that data is arranged into these tiny clusters. So basically, there are many clusters, and every cluster has just few reads. And we want to recover, and we want to do clustering. The trivial algorithm would be to compute all pairwise distances, right? If we would compute all pairwise distance between points, we would recover these clusters very well. The problem is that, I mean, so first, the scale of the problem is large. If we are dealing with billions of points, like, we cannot compute all pairwise distances, because if you square a billion, number just becomes too large. You don't want to get into trillions. And then eddy distance is also slow to compute. It takes quadratic time to compute it, although there are algorithms that estimate it kind of faster. There is basically a workaround based on locality sensitive hashing. So basic idea is that we use some family of hash functions that are fast to compute and that map similar strands to that are likely to map similar strands to the same bucket and dissimilar strands to different buckets. And a few iterative steps of using these functions and then kind of gluing the strands together once they're in the same bucket actually take care of clustering. So again, so that was very quick, but in the interest of time, I think that's where we have to limit ourselves. Now, let me talk a little bit about the cost of DNA synthesis and modeling it. So as I said, just using the bits per base density is not the right metric. And here is the reason why. So most of existing methods for DNA synthesis, including the new method that Reinhard has mentioned, they fall into the broad category of array-based synthesis methods. So what does that mean? So here is the mathematical model that you can have in mind for DNA array synthesis. So let's say that you want to synthesize 3 strands. So S1, S2, and S3. And each of them is just 3 characters long. So the first one is AGCT, the second is GCAT, the last one is CTAG. And so, okay, so how do you synthesize them? So there would be some kind of physical plate, and every strand that you want to synthesize would be assigned to one of the locations on this plate. And now you grow this strands character by character. So there is some kind of reference strand, some concept of reference strand. That's the kind of the sequence of characters that you flow over this plate. So first you would flow character A, and you would make it attached to the location where you want to grow the first strand. You would make sure that it doesn't attach to the locations where you want to grow the second strand and the third strand. And then you flow character G, so the second character in the reference strand, and you attach it to locations S1 and S2. So character C, you make it attached to all 3 locations, and so on. You keep going. So after 7 steps, after 4 steps, you would complete growing the strand S1. After 7 steps, you would be done growing the strand S2, and after 6 steps, you would be done growing the strand S3. So then what is the cost? So apparently the right way to think about the cost of this process is just the length of the reference strand. So in this case, the maximum length, like overall, there are 4 characters that we flow over the plate. So the total cost of growing all these 3 strands together is just 7. So the bottom line observation is that the cost of growing a pool of DNA strands is really characterized by the length of the shortest common supersequence that all the strands have together. So if you have 2 different pools of DNA strands, and for one strand the shortest common supersequence is short, and for the other set of DNA strands the length of the shortest common supersequence is large, then the first pool of DNA strands is much cheaper to grow than the second one. And that is something that has to be taken into account when we think about the cost of DNA synthesis, when we model the cost of DNA synthesis, rather than just the number of DNA bases that we use to represent our strands. And this can be taken into account when we talk about the design of our encoder. Like when we decide which strands we're going to use to represent our data, if we want to minimize the cost of synthesis, then we really have to think about the length of the shortest common supersequence that we have for this collection of strands. And another observation here is that really, like, one can use algorithms to optimize the cost of DNA synthesis as long as we are in this array-based synthesis methods. So, and batch optimization is one way to approach that. Like, even if one way or the other we decided that this is the pool of strands that we want to use to represent our data, in most of the cases the strands won't fit on a single plate. So we have to kind of somehow distribute them across multiple plates. And then there is room for savings in terms of deciding how do we make this distribution? How do we batch our strands that we want to grow across plates? How do we find the shortest common super sequence? Because all of these lead to reductions in the cost of DNA synthesis. So, and this is the subject of the recent paper that we have with that we have put out in December. Okay, so with that, let me conclude. So I touched on on the high level and on few specific aspects of optimizing the cost of DNA data storage. So again, as you all know, DNA data storage is an emergent storage technology. There are rapid advances in synthesis and sequencing, in coding for DNA data storage, in design of coding schemes for DNA data storage. So specifically, I think of this kind of new ideas in the space of using convolutional codes, and on this kind of better understanding of the cost of DNA synthesis and making it really a consideration in the design of the coding scheme. One thought that I just kind of, my personal impression about the space is that I think that it is too early to fix the encoding format, because just given how rapidly these technologies are advancing, and there is risk that we may stifle innovation if we decide that that here is the industry standard and that's how the data has to be encoded, because the error profiles change, new ideas in the coding space are introduced. So we really have to be careful about how we approach that. And one possibility that came out of brainstorming that we did in our group for that has been that, okay, so maybe one shouldn't really specify the encoding format, but maybe one has to specify the language for specifying the encoding format, because apparently this is something that has been done in other cases. So there is some language standard generalized markup language. So in the space of markup languages, this has been done. So like, instead of specifying the language itself, there is a standard that specifies the language for specifying the format. So if we could do something like that in the space of DNA data storage, this could also be greatly beneficial, I think. Okay, and with that, let me conclude and thank the organizers for the invitation.
Thank you very much, Sergey. You raised very interesting insights, especially the last one, which is the problem that all standardization committees, including JPEG, are aware of. The dilemma between waiting until everything is mature, which is often too late, versus the haste of standardizing something too early, and that this will be too early and maybe not adequate for the environment for which it is used. But this could be a very, very interesting topic of debate. What I propose is that, for the interest of time, now we close the part of the workshop that is the presentation by the three speakers that I would like to again thank for very insightful and very nicely targeted topics that bring new perspectives and new issues. Now, we usually stop the recording when time goes to questions and discussions. That also encourages people who are a little bit shy to get in. So the first thing I'm going to do is to stop the recording.